Massimilano Tamborrino from I'm lost, Warwick University. Okay. Many Italians, but around the world, plus a non-Italian who mimetize.
Can you see my screen?
Yes, we do.
Okay. Well, thank you for being here, despite being the last talk of the session. Well, good afternoon or good evening, depending on where you are, everyone. I'm Massimilano Tamborrino, and what I want to present is a work with Petr Lansky. The title of the work is Short Noise, Diffusion Approximation. And with Convergence, it's a kind of weird feeling to present this talk because it's a joint work with Petr, who recently passed away in April, and it's not so easy to do this. Petr has been more than a reference and a scientist person for me. I met him 10 years ago when I was a PhD student in Copenhagen. I spent almost 4 months in Prague working with him, where I also had the chance of meeting Ryota there and spent some time there. And since then, we have been working intensively, especially after I moved to Linz in Austria. We won a couple of grants together. We were visiting each other a couple of times per year, either in Linz or in Prague. And this is a work that we started when I was still in Linz, and we submitted last year, and has now appeared in Physica D this April. Okay, so the talk is devoted to Petr. I want to talk about the Poissonia Solenoid process. So imagine to have the following setting. We have some process which starts from some position x0. In case nothing happens, it has an exponential decay towards it. Alpha is the parameter determining the exponential decay rate. There is an underlying Poisson process NT, which is the one describing and moving the dynamics. So anytime there is an event coming, there is a jump. The jump has some random amplitude jk, where k is the kth jump. Tau k is the time of the jump, and these jumps are assumed to be modeled by non-negative random variables. They are IAD, distributed as some random variable j, and they are independent on the underlying Poisson process. If you are more familiar with SDE, you can rewrite this expression as dxt equal to minus alpha xt dt plus j dnt. And well, actually, why is the short noise important? Well, it has been initially proposed as a model for describing the membrane voltage in leaking integrated fire models. If you are familiar with the leaking integrated fire literature, this looks like a sort of Stein model where there is no inhibition, right? In the Stein model, you will also have plus j minus dn minus t, so plus some negative component pushing down. So if you think about Ryota's talk before, it is like saying that there are only excitatory postsynaptic potential. More recently, it has been used as a sort of building brick into more advanced models, like, for example, it is used to describe synaptic input currents in integrated and fire models or leak integrated fire models, as well as describing the conductances into conductance-based models. So in a way, the short noise process might not be definitely the most used and the most sophisticated models if you want to model the membrane voltage. We all agree on that, but it can be used as a relevant component into integrated fire and conductance-based models. What is important is that no matter which setting you are familiar with, no matter which setting you are interested in, the mathematical formulation of the short noise process is the same. So whatever I'm going to say later is valid, okay? So the setting of interest is the one where there is some underlying Poisson process NT, as I was mentioning before, and we are interested when there is some large jump frequency, or if you prefer, if you're thinking about, again, modeling this as excitatory postsynaptic potential, there are a lot of stimuli, a lot of currents coming. So there are a lot of them. The jumps are happening at an increasing frequency, and the amplitude of these jumps is decreasing. So if we have the jumps to be random, as in our setting, then it corresponds to say that the expected value of the jump amplitude decreases. A common approach corresponds to say, well, let us imagine that this jump frequency is large but finite. What we can do is to compute the underlying first and second infinitesimal moment of this discontinuous process and replace them by a diffusion process. So if we do that, what we obtain is this SD of this Y tilde solution, and you will immediately recognize that this is an Orsten-Uhlenbeck process, okay? Here, the drift comes from the interaction between the expected value of the jump amplitude and the frequency of the jumps. However, if you are also thinking about what I told you before, we are assuming to start from some initial position x0, which is positive. We know that there is an exponential decay towards x0, and the jumps are only going up, right? So that means that this non-negative Poisson shot noise process has a state space between 0 up to plus infinity, meaning that it cannot go below 0. So the Orsten-Uhlenbeck process, which has a state space R, does not seem to be a plausible or a good approximation. And so not surprisingly, when people were trying to replace the shot noise process with the Orsten-Uhlenbeck process into these more advanced models, they got a poor approximation. So what I want to do today is to derive a more mathematical rigorous approximation under some suitable condition that I'm going to define later. I want to show you how the derived model is going to outperform the approximation that we would have get by using the Orsten-Uhlenbeck process, and also give you a bit more of motivation why the Orsten-Uhlenbeck approximation is not the best one. I already emphasized the fact that there is a difference in the state space, but there are more mathematical motivation behind this. So in the following, I'm going to consider sequences of shot noise processes. Let me emphasize strictly that these are non-negative shot noise processes. So I'm assuming, once again, these jumps to be strictly non-negative, okay? And I'm in the setting where the amplitudes, the expected amplitudes of the jumps goes to 0 while their frequency goes to infinity. So this would be the classic setting of a diffusion limit if you think about random walk converging to a Brownian motion, okay? So the two questions that I want to answer are, the first one is, what type of limit process do we get for such a sequence of shot noise processes? And moreover, if we do not care about the limit, but we want to work with a large but finite jump frequency, what could be a better approximation than the Orsten-Uhlenbeck process, okay? There are a few results. Basically, you can manipulate the original shot noise process in a way of getting any sort of limit, depending on what are your interests. But what I want to do is to work with the original shot noise process. So I don't want to do any sort of manipulation like subtracting the drift and rescaling by the standard deviation and so on. So the outline of the talk, I first want to recall different types of limits and approximation. This is particularly relevant because when I first got introduced to the topic with Petre, I was kind of confusing because when reading different papers, they were using the same notion of, well, the same name of diffusion approximation for quite a different notation and quite a different notion. So I want to reconcile this. Then I want to derive the so-called weak convergence of the sequence of short noise processes, and I will define in a second what does it mean. I want to characterize the feature of the limit process, and then I want to discuss under which condition the sequence of short noise processes can yield a diffusion limit, so we can get this back, this Orsen-Uhlenbeck process. I want to compare the different approximation, and then if time is left, there is an open conjecture that we weren't able to prove, so hopefully you can help us on this. So what I was mentioning before is what we define the usual approximation, and is based on the idea of basically equating the infinitesimal first and second moment of the discontinuous process with a diffusion process, okay? And if you do that for the short noise process, you will recover the Orsen-Uhlenbeck process. So in this case, no limit is taken, you just equate the first two infinitesimal moments. If you are also imposing that the diffusion process has to be a Gaussian process, we have what we call the Gaussian approximation, okay? So in the case of the short noise process, both the usual and the Gaussian approximation yields, in fact, an Orsen-Uhlenbeck process. Part of the confusion I had in my mind, but also talking with other colleagues like Magnus Richardson, but also Benjamin Lindner, was the fact that these two types of approximation are sometimes known as diffusion approximation in our community, as also, for example, in the mean field community. While I had in mind a different notion of diffusion approximation that I will explain in a second. So to avoid this confusion, I refer to this type of approximation where basically you want to equate the infinitesimal first and second moments as usual or Gaussian approximation. The third type of approach is the one that yields the fluid or the thermodynamic or the hydrodynamic or the hydrodynamic limits, or also the Langevin approximation or Kurz approximation. Once again, for fixed n, you are equating the first two infinitesimal moments, but then the difference is that if you do the limit and n goes to infinity, what you are going to obtain is a deterministic process. So if you do, I mean, this is also quite common in mean field theory. You have a lot of neurons, capital N. You approximate this collection of discontinuous processes by a diffusion process, and when n goes to infinity, you will obtain back the deterministic process. So this is also sometimes called as the Langevin approximation or the Kurz approximation. But this is also referred as sometimes as diffusion approximation, which makes, again, everything a little bit more confusing, okay? So from a mathematical point of view, what I want to study is the so-called weak convergence of stochastic processes, which corresponds in studying those triplet of characteristics that Bruno was introducing in his talk. And it's a mathematical way of saying, well, let us look at this process on itself and what does it happen, how this process converge in terms of law, so the distribution of this process when n goes to infinity. And you either prove it via the convergence of triplets of characteristics, as is proved by Jacob and Shirayev, or you can also show via the convergence of the finite dimensional distribution and some regularity condition like the tightness, okay? So this is the most mathematical approach somehow. It can yield any sort of limit. There is no condition, no prerequisite on the type of process, limiting process that you get, but it's not that easy to handle. Another approach is the one that we refer as diffusion limit, but it was initially proposed, initially called by Richard and his co-workers, including also Laura, as a diffusion approximation. So if you have a one-dimensional process, as we have, proving that proving the weak convergence, so proving the convergence of these processes via the triplets of characteristics, can be done in a way easier and way more manageable way, but just looking at the convergence of these finite dimensional moments. Okay, so in particular, you have to show that the first and the second infinitesimal moments converge to the limiting process, and that the fourth infinitesimal moment vanishes. The fact that the fourth infinitesimal moment vanished means that the limiting process is going to be a process with no jumps. So it's going to be a continuous process, meaning that you are going to get a diffusion process. So this is why it's called diffusion limit, or in a way, weak convergence to diffusion process. But it is also known as diffusion approximation. But you will agree with me that this notion of diffusion approximation is different from the previous one. Here, there is a rigorous mathematics limit, and if under some condition, you are going to get a diffusion process. In the previous approach, in the usual or the Gaussian approximation, such limit does not exist. You are only comparing infinitesimal moments. And in what we call Kurz approximation, when actually you do the limit of n goes to infinity, you obtain a deterministic rather than a diffusion process. So we are interested in deriving the weak convergence of these sequences of short noise processes. And well, the previous component, this J, D, and T, could be replaced by a component Poisson process with some Levy measure that is basically nothing else than the product between the intensity of the jumps and the distribution of the jumps. So the frequency of the incoming jumps of the Poisson process and the distribution. And if you do not really like to think about the measure, you can think about the density, where basically you replace the CDF with the PDF. Okay. So what we were able to show is that if the intensity of the jumps goes to infinity, and the Levy measure of the sequence of the shot noise, so the Levy measure of this compound Poisson process, converge to a Levy measure, what we get is what we call, well, what is known as a Levy-driven or Uhlenbeck, which is the solution of this STE, where now the compound Poisson process is replaced by its limit, where this limit is characterized by a Levy measure, which is the one obtained by doing the limit. So things seems quite hard, but in fact they are very simple. You take your jump distribution, Jn, you compute its density, you multiply this density by lambda n, so by the frequency of the jumps, and you do the limit when n goes to infinity. Okay? If you get something finite, this is going to be the Levy measure of your limiting process. Okay? And actually it's going to be the Levy measure of this L infinity, which is also known as the background driven Levy process, because it's going to act as a sort of underlying noise. That's why it's called background driven. Okay. What we show, which is somehow not so surprising, it's relatively intuitive, is that such a limiting Levy-driven or Uhlenbeck is not a Gaussian type. What does it mean? It means that the underlying Levy process is not a Brownian motion, meaning that this process is not an Uhlenbeck. So it's not a Gaussian Uhlenbeck, but is a non-Gaussian Uhlenbeck. Okay. In particular, one can show that it is not true that this Levy measure converges to zero. Well, we will need the convergence to zero to show that actually there are no jumps. So the process is a continuous process, so a Brownian motion. Okay. So if we do this theoretical rigorous approach, we ended up obtaining an Uhlenbeck process, which is very similar to the one that we are used to, but where the Brownian motion is replaced by this Levy process. We are able actually to characterize this limit Levy-driven or non-Gaussian Uhlenbeck process. We are able to compute its mean, its variance, covariance, but we are also able to compute the characteristic function. So one may numerically invert it to get the PDF of such limited process. And you see that, well, if you look at the corresponding quantities for the shot noise, they are very similar, with the difference that this quantity here are replaced by lambda n, the expected value of the jumps, and lambda n the expected value of the second moment of the jumps. But what is important here is that this L infinity 1 is the this background-driven Levy process at times 1. So how can we study it? Well, as you may imagine, and also as we know from here, this underlying Levy measure fully depends on the distribution of the jumps. So what we have is that, well, if the initial jumps are Poisson or Bernoulli distributed with some certain parameter, we can obtain that the underlying Levy process is a Poisson process. If the jumps are gamma, we obtain a gamma process, inverse gamma process, beta process. So since the underlying processes are like this, we are going to get the non-Gaussian Orsten-Uhlenbeck is a Orsten-Uhlenbeck Poisson process, which is in fact a different shot noise, or gamma process, inverse Gaussian, and so on. Thanks to this, we are able to explicitly derive the first and the second mean of this quantity. L infinity 1 is going to be Poisson, gamma, or inverse Gaussian distributed, depending on the different setting. A first tricky thing to realize is that if we think about the gamma process or the inverse Gaussian or the beta process, they are infinity activity processes. What does it mean? It means that no matter how short you are considering your time interval, there are infinitely many small jumps happening in that interval. So what does it mean? It means that if we integrate the Levy measure, it's not finite, but it's infinite. So in this case, what one does is to introduce a sort of CDF or survival. So you are going to integrate the Levy density, and this quantity, which is called the Levy-Khinchin tail function, is going to be finite. So what does it mean? It means that if we take any small quantity x larger than 0, the rate at which jumps are of size greater than x occur is always finite. But the tricky thing is that since there are these processes which have infinity many small jumps in any time window, it might be tricky to simulate them. But luckily, this is not the case thanks to some results by Ku, Dacios, and Zhao, who were able to propose some exact method for simulating these Orsten-Uhlenbeck gamma process and Orsten-Uhlenbeck inverse Gaussian processes. So what I did was I luckily got the MATLAB file. I made it an RCPP, so just to speed up the simulation. And then there is a GitHub code available here for simulating both the shot noise processes with the different jump amplitudes, as well as the limiting non-Gaussian Orsten-Uhlenbeck processes. What you see here is that, well, the red line is the shot noise process. The black line is the simulation of the Orsten-Uhlenbeck gamma. They seems to behave similarly. It seems like also the shot noise has some very small jump amplitudes. But if we zoom in, we see that this is not really the case. So we can see that for the limit Orsten-Uhlenbeck gamma, there are in fact a lot of small jump happening as well as large jumps, while this is not the case for the shot noise, because we are in a setting where the intensity is small. So if we let lambda increase, then we will observe a more similarity between the shot noise and the limiting Orsten-Uhlenbeck process. And let me just, well, I don't have that much time left. Let me just emphasize what are the conditions for obtaining a diffusion limit. Well, if we want to get that the Orsten-Uhlenbeck is the limit of a diffusion approach, so it's a diffusion limit, we need to require that these 4 conditions are fulfilled. And we have already seen that if this is possible, then we will have get the Orsten-Uhlenbeck as a limit, and this is also the result of what I call the usual of the Gaussian approximation. But before I told you that this is not the case, so I told you that this limit process is not going to be Gaussian, meaning that at least one of these 4 conditions has to be neglected. Well, at least one of the 4 does not hold, okay? So all 4 conditions do not hold simultaneously. This is our conjecture that unfortunately we were unable to prove. So if you have any idea on how to prove that you cannot find a non-negative sequence of random variables and a sequence of numbers lambda n such that these 4 conditions are simultaneously fulfilled, just get in touch with me, okay? Let me just show you the quality of the approximation. So what you see here are different results obtained via simulation of 1 million, well, 1 million Monte Carlo simulation for lambda equal to 1000. And what I'm reporting is the estimated density of the shot noise in black, the limiting non-Gaussian or Stern-Uhlenbeck process in gray, and the Gaussian or Stern-Uhlenbeck process in blue, when t is equal to 1 and when t is equal to 100. So the setting t is equal to 100 is under the idea of being an asymptotic regime, okay? And what we see is that the simulation coming from the limiting or Stern-Uhlenbeck, non-Gaussian or Stern-Uhlenbeck are nicely fitting the shot noise, while the Stern-Uhlenbeck is far off. We are able actually to compute the quantity of interest of the, particularly the Levy measure, the mean and the second moment of these processes as a function of the initial jump amplitudes and as a function, as a function of the intensity and as a function of the parameters of the jump amplitudes, meaning that even if you do not want to run the limit because you are interested in a different type of approximation, you now have a way of replacing the shot noise for a finite but large value of lambda n with this type of non-Gaussian or Stern-Uhlenbeck processes, okay? Well, here is a bit more of what I was saying. Let me just conclude with one final remark. There is actually a way of getting an Stern-Uhlenbeck as a limiting process, and it's kind of cheating. So right now we are having jump amplitudes that were only positive. So we were imagined to have jump amplitudes that are positive with probability 1 minus Fn and negative with probability Fn. Right now we were saying, well, Fn is equal to 0, so we have jumps that are positive with probability 1. Now imagine to allow for having negative jumps with probability Fn, and Fn goes to infinity. Well, you can trick it a bit, you can play around, and we were able to show that you can find some positive and negative jump amplitudes such that all these 4 conditions that are those yielding a diffusion limit are met. So by allowing the possibility of having negative jumps happening with a frequency with probability going to 0, you're able to recover the Stern-Uhlenbeck process. And the trick behind is that you can show that allowing that corresponds to having a sort of generalized time model, which has been shown by Petri and others, that in the case where these jumps are actually constant, it has a Stern-Uhlenbeck process. So that's the way of cheating by saying, well, Jn is not anymore a positive quantity, but it's a real value. So that's why you get back to the Stern-Uhlenbeck process. So as usual, I'm talking too much. I stop here. The paper has been published on Physica D. This is the reference for the code in case you're interested. And well, the main message, or one of the messages, is that we are coming from a different community. We have a different background. Maybe we should be careful when we talk about diffusion approximation, because Dev will have saved me a couple of months getting through the paper and say, no, that's totally wrong. That's totally wrong. That it doesn't make sense. And then realizing that it was a different idea, a different meaning, a different notion. And other than that, the selling message is that if you want to approximate the shot noise with something else, maybe instead of using the Gaussian or Stern-Uhlenbeck, you might use these non-Gaussian or Stern-Uhlenbeck processes, and some characterization of that are available in the paper. Thank you for listening.
Thank you, Massimiliano. I see a first comment from Cindy Greenwood. Cindy, please.
Thank you, Laura. I want to say that I also had the privilege of working with Piotr Lansky. I appreciate this talk very much, Masi. You did a great job.
Thank you, Cindy.
And I think I can see the hand of Petr Lansky in this work. One thing that I very much appreciated in working with him is his way of looking again at something that has been many times passed over and finding something new and interesting. It's just amazing. Beautiful example of this. Thank you, Massi.
Thank you, Cindy.
I absolutely agree with Cindy. Let's say that this session can be partly dedicated to Peter, because here we have Riotta and Massimiliano, who were his collaborator for many years, as well as I was and you was, and I see there is Susan and many others that have long story with him, and we learned a lot from him, reading better all paper also. Are there other comments or questions?
Can I ask a question to Massimiliano?
Yes,
Yes,
sure.
please.
Please.
Can you show me slide number 7, Massimiliano?
Yeah. Yes.
There is the main theorem.
Yeah.
Yeah, okay. So this is 8. Go the slide before.
Sorry, I was messing up with the Zoom.
7. That is the point. So here you are saying that, okay, the random variables j, k are non-negative, true?
Mm-hmm. Yeah.
So it means that your limit process, capital L infinity, is always a subordinator.
Yes.
Okay. So, and what do you know what are conditions so that the Levy measure of the so in condition on J, so that the Levy measure of the limits subordinator is infinite?
Well, not really, in the sense that this happens. This happens for the gauche, for the gamma. So if the initial jumps are gamma, or
okay, maybe not necessarily on the J con E, but on the limit, because the parameters also is relevant to get an infinite Levy measure.
Yeah. I don't really know. Well, I mean, in the case of the only case where we do not get this is for the Bernoulli or the Poisson jumps, which has a kind of unit jumps, while in the other case, this was not true. But one possibility might be related to the behavior of the second infinitesimal moments.
Okay, but okay, suppose that
I'm sorry, they are asking to free the channel. I have to ask you to continue the discussion privately.